But then you at least have to have a multi-thread, multiple user level threads. And in that case, you need a yield. And so once you have yield, things get actually already a little bit tricky. So the point is that when you attack this kind of a problem, you are forced into a situation that you have to say, oh, from the very beginning, I have to be able to deal with all kinds of concurrency. So the underlying module from the beginning could potentially have very complex interactions. So then you have to think hard, what kind of a fundamental abstraction you are looking for when we look at any single piece of a code fragment or code components. So the idea is we use this thing called certified concurrent abstraction layer, try to untangle this mess. So we will have these abstraction layers that Ronghui has already talked about yesterday. We try to do the horizontal composition. We try to do the vertical composition. We try to use a compcert-X, which is verify the compiler, compiles them into assembly level abstraction layer. You do the linking at the assembly level. You use some beautiful parallel composition construct to compose these things together. Okay? So that's what a certified concurrent abstraction layer is. And you use this technique to compose things to build an OS. So in order to understand the underlying construct, I will start to slowly work through this example. So it's very important you understand every single line of code on this slide. I will work through it box by box. Okay, so if you have any question, you should stop me now, and otherwise, you will not follow the rest part of the talk. So let's start from this main client program. So we are running two threads. One thread running on CPU 1, and this thread, all it does is make a call called update X. And another thread is running on CPU 2, and it's calling also the update X. So this client program is actually running on abstraction layer L2, which implements a primitive called update X. I assume you guys have listened to Ronghui's talk yesterday, so you already know a little bit about the abstraction layer. So that layer provides a primitive called update X. This update X is implemented by underlay L2, which is implemented by module M2. So this M2 is implemented on top of abstraction layer L1. Okay, that L1 provides these three primitives: acquire, which is acquiring a lock. Remember, these are two threads running on two different CPU cores. And one calls, there's a primitive called acquire a lock. Another is called release a lock. And then there's a primitive called CPU ID. And so what this void update X does, M2 module has a private variable. Well, it's actually a shared variable, X. And so update X will acquire the lock. This lock protects this value X. Update X will first acquire the lock, then increment this X by the CPU ID. If CPU ID is 1 and 2, then one would increment it by 1, another will increment by 2. Okay, and then release the lock. So that's what this update X does. And you have two threads, each running on separate core, and calling this update X function. And then this abstraction layer L1 is implemented by this module M1. And so it implements these locks. So the lock, we can't just use standard spin lock, because spin lock does not provide liveness. We actually use ticket lock. Just to remind you what a ticket lock does, is a ticket lock actually always contains shared variable n and t. They are unsigned. And so this t contains the ticket, and n is probably associated to this lock n. So you don't have to worry about this particular variable in these examples. Just view that this every lock contains a ticket value t. So what you are trying to do is when you acquire the lock, you are going to fetch and increment this ticket. Just like when you go to a bank, you first fetch your ticket, right, and it print out a new number, then you wait there until your ticket number is called. And that's exactly what this ticket lock acquire does. First fetch and increment the ticket value. This FAIT is a primitive provided by the underlay layer L0. And then you read this ticket number until this value is equal to your ticket number. Then you exit this while loop. Otherwise, you keep execute this loop. You keep calling get n. When you are done, when actually it's your turn, there's a low-level primitive called hold that basically indicate you are now holding the lock. You can now actually access this shared variable x. Okay, and the release will actually increment the ticket number and does nothing else, and then essentially release the lock. Okay, so those are the acquire and the release, and the CPU ID is probably forwarded from. It's a primitive provided by the underlying machine. So that's the high-level picture of a simple concurrent program that contains a lock implementation. And what I'm going to show you is how do we use certified concurrent abstraction layer to reason about these things. So are there any questions about this example? Any line of code on this slide that you don't understand?
What does hold do?
So hold is a primitive, ghost primitive we introduced to indicate that we now hold the right to update x. Because you cannot actually, if you need to call this function in order to update value x, otherwise you will get rest conditions. Okay?
In which sense it is ghost?
It's not a really ghost. I'm only saying that the logically, it basically, by calling hold, we essentially says, what it does is, the proof will see this hold as a way to acquire the permission to update x. Okay?
So,
yeah.
So it's like updating the logical state instead?
The actual underlying mechanism a little bit more complex than that. We use what we call the push-pull model. So view it more like hold as a way to. So instead of modeling shared memory as a single thing that you acquire permissions, you actually view that each thread has its own local copy of the same shared memory. And so when you call the hold, you actually invalidate the permission of the shared copy. You copy the shared memory into your local copy, and then you make the shared version invalid. And now you have this local copy that you can update. And then when you release the lock, you actually have another push operation, which essentially copy this value back to the shared location, and then you make that shared version valid again. And all these are for logical reasoning. The underlying implementation is still only have one copy, and you do the updates.
So it's kind of in separation logic resource management operations that allows you to transfer resources from. That allows you to have.
Yeah, it's like ownership transfer in separation logic. And again, we find the ownership transfer very hard to reason for refinement-based mechanisms. So we don't want to see data transfer from a block of things moving from one place to another, and instead we just copy the value, and you don't have a resource transfer. Okay, that makes the refinement much easier. Okay, yeah.
Can you enforce the user to release the lock?
No, you cannot. Incooperative user will always, you can acquire the lock, never release the lock. And so that'd be bad. Fortunately, we are verifying the kernel, and the kernel is written by us. So if you don't release the lock, then you cannot link module together. Because in order to make these different pieces, mixed together, composed together, you have to, the other side will assume you will release the lock. So if your code didn't release the lock, then you cannot really compose them together. Okay? Yeah.
So you immediately validate the shared data after call?
Yeah.
Or
It's in a single primitive. It's in the single primitive hold. Yeah.
Yeah, but is it for reads also? I mean, you.
No, not for read. You only do it at a lock acquire and a lock release. When you acquire, you copy.
You can acquire the lock and read the shared data.
No,
read the shared data. Or?
No. When you acquire the lock, you copy the shared data to your local copy. When you release the lock, you copy the local copy to the shared data. Just like git pull and push, except at any single time, only one user can do this. And once you pull something, that shared copy will become invalid. And only when you push back, it will become valid again. Yeah, yellow shirt in the back.
So the C implementation of hold will not do anything, right?
The C implementation will not do anything. This hold is a no op. Yes. Yeah.
What's the relationship among all the three layers? Do they share any variables, global variables?
You mean between these abstraction layers?
Yeah.
No, they don't.
Do they have any dependencies?
Of course, P, you can see this P builds on top of this layer L2, which provided this primitive update. And this update builds top of this layer L1 because it calls acquire release CPU ID, which is provided by this module M1 built on top of L0. So it's kind of a set of objects, one builds on top of another. So the Certicos's vision of the complex system in the future is they are all built on top of these, a set of objects stacked from bottom up, and one built on top of one another. Okay? Yeah.
Anything in L0 depends on the upper?
No. No. All right. Everybody understand this code? All right. So now we try to verify it. Or first understand how this code works. Right? It's already pretty complex. So I want to explain this notion of a strategy, which is a game semantics notion. It sounds scary, but it's actually not very different from what you guys normally understand as a trace or program trace. It's just a very special kind of a notion of a trace. Okay? So this basically says how the program P will generate events on behalf of CPU I at every step regarding a given log L. Okay, so the log L, again, the actual runtime execution does not generate a log. We could generate a log. That might make it more like a blockchain. Okay, but right now, when we build this concurrent program, we don't actually build any physical log. But we nevertheless use a ghost state or logic state, which we call it logic log or log L. Why is that? Well, anytime you have a concurrency and you have multiple threads interact with each other, you need to know what the other guy has been doing things. And the best way to communicate what others have done is to use logs. Because if you only maintain the shared state, don't know the history, then you don't know, who has done what. If you have logs, then the concurrent code becomes just a coordination scheme where every thread contributes some events to this shared log. So this log becomes kind of just append only the definition of log. You basically are growing the log. Every thread is throw some new events onto this log, and they actually are very compositional because if you have n threads work with each other, then each thread will just throw some events onto it. Okay, and so in order to turn a concurrent program into a sequential program, so that you can use traditional while logic, you try to model the notion of a strategy, which basically says, oh, if you give me a log L, which essentially says what are the current state of the shared variables by replaying the events in the log, my program P will generate these additional events. Let's assume currently we are running on CPU I. So we try to use this kind of a diagram to model the kind of things we want to explain. So if your particular program, this says I have a fetch on write function, fetch and increment function executing on CPU 1. okay? And the question mark L says, given a log L, okay, I will put this new events, which is executed by thread 1, running on CPU 1. It will be a new event, FAIT, and so this is just the event name, fetch and increment event. Let's assume we introduce this new event. And the return value of the current ticket values, okay? So let's assume that before calling this particular fetch on write functions, you already have two, the thread 2 has already added these two events onto it. Then this diagram, this particular strategy diagram basically says, well, if you give me log L, then this fetch and increment primitive will generate a 1.fait event onto this log and return the current ticket value. This is the ticket value before you calling this primitive. So previously it's incremented twice, assume it started from 0, so it should return 2. And if, for example, this is the initial log, when you call this 1.fat, then the value will be 3. So this $t is the return value when you increment this event. And this is how the logic log L will grow. And if you want to find out what are the current value of the ticket, you just replay this event. You would say replaying this event is super slow, but who cares? We are doing it for formal reasoning, right? So one of the key idea of doing formal verification is to understand what is actually code run at runtime and what is actually code helpful for reasoning. One of the major problems of existing formal framework is that people like to use the ghost variable, ghost state, but they are very conservative about adding these ghost variable, ghost state because after all, they are called ghosts. Why you want to have that many ghosts? My group's work was saying they are not ghosts. Those are the real things. That is, when you write a program, the logic specification is the program you are writing. And the whole game is to try to write in a way so that you can do the proof, and only some part of it is actually the realizer or the actual code that implements the spec. So you will find that in the Certicos project, we aggressively add huge number of these ghost state. And in fact, the more we move forward, you will realize that the whole game of writing certified software is writing spec. The spec will contain many ghost state, but they should not be called ghosts. They are the state, how do we understand things. And one of the reasons concurrency is hard to reason is because we are stuck with these super optimized versions that needs to run on the machine, and we avoided all these auxiliary logic data structure like logs, so that it can be implemented. It's almost, it reflects what the current language can support, where the certified concurrent abstraction layer essentially try to show you that if you instrument all these objects with sufficient logic data structure, then the picture of how concurrency works becomes very obvious. And as long as you identify what is the logical, what is the physical, the underlying code will still be same. So this shows what a fetch and increment would do. It's a primitive that...
Change the battery of the microphone.
Okay.
If you just go for 1.
Sure. Now you can ask me private questions. Off the record.
Or can I just
Okay. Right, but not the most recent version, which is still undergoing lots of cleanup and improvement. So, but we do want to eventually release it. Right now, the version of our proof is still for these older version of Coq and the CompSert. So we need to move it into the latest version.